Welcome back. I'm Dominic. This is episode 3 of my adventures in repairing the Tektronix 2465 ADV oscilloscope. In the earlier episodes, I discussed how I got into these repairs. There was a reefa blowout, and the fan was damaged in that blowout, and so I've replaced those things. One of the electrolytic caps was also replaced, and it now turns on just as you see in the picture here, but after maybe 5 to 8 minutes, maybe 10 minutes, it goes into a power wind down. So I'm going to describe in this video just how I used a Datalogger to start tracking that down. And so again, on archive.org, if you type 2465 SVC, you'll get to the service manual. On page 260, all the way to the right, you will see all of those voltages that I marked in red asterisks here that I'm interested in trying to record during the first, let's say, 2 minutes, to see what goes out of range during the entire 2 minutes prior to when the power wind down occurs. I'd like to track down this problem before it actually goes into the power wind down. One thing you can notice in this schematic is on the plus 15 rail, there's a place where a little encircled plus 19.2 volts. Yeah, I've been recording that. That goes to the fan. At that junction, it's actually 19.2 volts. Now, these unregulated voltages, they continue on to page 263, where you see the circuitry for the regulated voltages. And those can be accessed on the bottom of the oscilloscope on the A1 main board at J119, which I will soon show you a picture of. Now, in addition to all of those voltages, they span quite a spectrum. It goes anything from minus 15 to plus 87 volts. All but one are analog. So there's even a digital channel in here. So that's quite a lot of voltages. So a Datalogger is to me a pretty straightforward choice if it can work. Now, on page 112 of that same service manual, table 5-1, you can see the various voltages that can be accessed there. The readings column, that shows you the range of values where that's possible to enter into the settings for a Datalogger. So each channel is differential, so you can put in a lower and a higher voltage range, and so each of the channels will be recorded similar to just an oscilloscope, except these can go on for many minutes or hours if you need. On the main A1 board, the picture here on the right, you can see what that J119 looks like. It's a 14-pin socket. Very nice. I've marked the number 1 position. These are numbered exactly the same as a modern integrated circuit. So it goes from 1 to 7, then it continues opposite 7-pin. There'll be 8. You count back up to 14. Very nice. I wish there were more instruments that had this kind of a feature. Very, very nice. So this is the Datalogger I used, which is the cheapest one I know of that can do this work. This particular one, the Datac DI1120, unfortunately it's obsolete. You could probably find some used ones around. Anyway, as I said, they have, this particular one has 4 analog channels. It has something like 7 digital channels as well. They're differential, kind of. The voltage range here is plus minus 2 out to plus or minus 100. In other words, all of the possible voltages I could want to measure on this oscilloscope are covered by this instrument without any modifications. The input impedance is 795 kiloohms, a little bit lower than most oscilloscopes as far as I know. As a millivolt reading for a multimeter, those go up to 3, maybe even 10 gigaohms, so it's a little bit low for like nanoamp leakage current measurements or something like that, but I don't need that here. Absolute maximum input, we're fine. The common mode range, you have to be really careful with these devices. So this 2-point specifications, that's just copied straight off of the manual. In the red box here, I've written down some additional things I think is nice to look at on the same slide. So 40 kilohertz on each of the channels. So if you're only using one channel, you can configure it to as high as 160 kilohertz. But 40 kilohertz I think is going to be fine for this particular oscilloscope. The 12 to 14-bit resolution is typical for these types of devices, which is why we, in my other work, usually like with physiology, we kind of like these things. They're cheap and they go in lots and lots of channels. These are easy to find with 8 to 16 channels, not super expensive. The USB devices, which means that you can record onto a notebook computer, where the notebook computer can be running off its battery, which means it's isolated, so you don't have to worry about ground loop issues. Very nice. You can export with the software that comes with this thing. It's Windows only software, but you can record to CSV files, which you can then immediately open in our programming language to do any kind of analysis you want. And that's how I typically work. Now here's how these things differ from an oscilloscope. It is voltage over time, but watch out. The USB chassis is one ground. The ground pin on this terminal leads is another, and then the minus terminals for the analog channels is yet another. And there's resistances between these, and when it's turned on there will be voltage differences between these. It's only a couple volts at most. I think it's 1.5 volts or something like that, but there's also resistances between these. So the way these things are built, it's very different from an oscilloscope. That minus pin is not ground, and there's resistance between the positive and the negative leads, which means that they're somehow connected internally. You can sort that out if you look through the manual. Sometimes you even find schematics with these devices, and you'll understand why. But that means you have to use a bit of caution using these. Now, what I did to stay away from common mode issues is, if you look at the picture on the right, you'll see these little metal wires that stick out from the minus pins terminals, and those are all soldered together, and then they're all fastened to a black wire of pretty high gauge, or maybe I said low gauge, a thick wire that goes around this black wire, dropping from the bottom of the Datalogger. It kind of continues behind the oscilloscope on the right side of the picture, and that is both screwed onto the chassis of the oscilloscope. The measurement of the voltages on this oscilloscope are referenced to the chassis ground, which is earthed. Okay, so you have to watch out a bit on how you make these recordings. I use a 1 kilo ohm series resistor on these leads, where the resistor side is on the J1919 test point. And I'll leave that as an exercise for the student, why I use that resistor. I have a number of reasons why I did that, not just one single reason. But if you happen to be an engineer, technician, you immediately speculate why I could do this. But I think it's good to leave something as a little bit of a mystery, so we can get on with the other discussions here. For those of you who use Linux, me included, there's Python USB. If you use that, it means you will escape issues with having to use this mode button on these devices. The mode is made so that you can use open source software if you don't want to use their proprietary software for Windows. But if you push that button, you could get locked out from getting back into the Windows software. So I try not to ever use that button. So instead, if you use the Python USB utilities, you don't have to use that mode button, which is very nice. Now, I've listed some modern equivalents. For the DATAC, the 4208-U is what they're recommending. That is many times more expensive, and then you have to buy the software to use the channels, the analog channels. I don't know why they did that. The cheapest one they have is either the 188 or the 1100, which they're not quite as good as this one, but they could maybe work. ElectroKit in Sweden has a completely different brand. The article number is here. That's an 8-channel device, 12-bit, and it uses the I2C protocol, which it means you're going to have a little bit lower bandwidth, but it could maybe work. Now, here is my setup. All the way on the upper left, you can see the computer screen. Because this is a USB device, the Datalogger outputs to the computer I basically get everything on this big giant computer screen. It's like having 4 giant oscilloscope screens where each channel gets its own oscilloscope window. It's very nice. I like that about these data loggers. I have the logger set on a lab jack, so I can get it just to the right height so that the data logger is right smack in front of the J119 test point. So you see the leads kind of crawling over the DATAC. On the other side is where it connects to the J119. The auxiliary fan, it's situated underneath the scope, and that helps to cool the U800 IC, which I heard can get quite hot and cause power wind down issues. So it's got its own separate fan hooked up right there. I use a mechanical timer. These are 2-minute recordings that I like to do, and I can actually hear the timer, and I can check it once in a while just visually, without needing to look at any electronic device, turn on a phone or something like that. So it's convenient for me. I use a thermometer, 2 probes. The TH1, that is situated right in front of this new fan. Now, the fan blows out, which means that it's situated just in front of the A2, A3 power supply boards that I just repaired. And any heat generated from those power supply boards, like anything that's like maybe the thermal cutoff switch or something like that, that heat goes right through that fan, and it goes right across that TH1 thermometer probe. The TH2, that probe is sitting on top of the A5 board, where I have some ICs that tend to get kind of warm, so I can see that measurement separately. I also have a watt meter. So this thing typically is somewhere around 98 watts when it's working properly, but during my recordings I can actually see if there's sudden swings in the watts that warn that I've got a short circuit, or it's starting to go into a wind down mode. So that being said, here are some recordings. Now, these are 3 separate screenshots, and so each screenshot you can see 4 channels being recorded. These are in this case all analog channels. And if we take the upper left image here, you see the 4 channels that have been recorded, and you can see first of all that if you look at the plus 19 volt unregulated, that's the one that goes to the fan, unregulated. These little spikes that go down, I think this is relay switching or something like that. I can actually hear these relays switching on and off, and you'll notice that those spikes are not seen on any of the regulated voltages. Now, this red bar, the vertical bar, that indicates the end of the diagnostics step, just when it is first turned on. Now, I'd also point out the fact that at the beginning and the end of these traces, there's nothing. There's just empty squares. That is because I start the recordings before I turn the oscilloscope on. I make the 2-minute recording, and then I turn the power off, and then I end the recording. That means I see everything from the time I turn it on until I turn it off, and I can have basically some kind of control that I'm actually sitting at 0 volts. Everything's calibrated and so on before I turn on the scope. Now, on the upper left screenshot there, the plus 19 unregulated one, again, that's the one that goes to the fan. That second circle where you see the voltage jump up, and it looks like a noisy recording. What I did was I disconnected the fan, but I left the recording going, so that the data logger is still connected to the plus and minus pins of the power supply. And what I see is how the voltage goes up. So I see how much voltage the fan is pulling, and so by disconnecting, the voltage goes up a little bit, but you can see that the swings in the voltages look just exactly the same as before I disconnected the fan. So whatever that is, it's not coming from the fan. In the other traces or screenshots, you can also see that those same switching behaviors, and they're always unique to just that unregulated channel. The regulated channels don't show any switching noise. That's kind of nice. Now, on the upper right screenshot, have a look at the -8 channel. Now, the plus 10, the plus 15, the -8, in fact, all the channels here, they're scaled to the tolerances that I showed you for table 5.1. And so the only one that you don't see coming into range where it should be is the -8 channel. Now, I believe that this could be an explanation for things like a test 0540 fail 40 error. Test 05 fail 40, I believe. You'll notice that it never gets down to -8, which means it's a higher voltage than it should be. Okay, test 05 fail 40 means unexpectedly high voltage, or inappropriate high voltage somewhere, and that might be the explanation, maybe. I've mentioned, by the way, the X and Y axis scales, they're written here if you need to go back and have a look at that. So I zoomed in on that upper right trace. I zoomed in at just the last second of the recording. And so here you can see what I see close up. And the +10, the +15 rail, you'll notice that there's not any particular ripple. But in the -8 channel, there is some ripple, and it happens to be 100 hertz. So there's something from the mains rectifier that's making its way all the way through the -8 unregulated and right down to the regulated -8 volts. And you'll notice another thing about this is that this voltage here, I've written it down here. I know that the fonts from the software are really tiny. This is -7.5 volts, so it's never getting to -8 volts. So two things happening. I'm seeing this kind of AC ripple-like thing after a rectifier. I'm in Sweden, so we have 50 hertz, so it's double after the rectifier, 100 hertz. The +19 channel, on the other hand, now that might look like some kind of aberration, but if I went in and looked at the values that here, and that ripple, it amounts to 65 millivolts out of 19 volts, and it's on the unregulated side, and it's 240 hertz. So I think this is some kind of switching transistor or something that goes to the fan that's not a problem. So I'm most interested in the -8 channel then. So going back to page 260, where I have the schematics on the right side, I'm zooming in here just on that -8 unregulated, and I had a look, and I'm very suspicious about this C1102 cap. It's 100 microfarads. I marked it with a red asterisk. I'm probably going to replace that next. Now, if you look at the right side, that's an image from page 256, where you see the components mapped out and on the board, and the sun symbol, that's the C1112 electrolytic cap, which I replaced. It was leaking all over the board, which is why I replaced it. I thought I did okay job cleaning, not spectacular. Everything seemed to be working when I put it back together, but now that I have this power wind down issue, looking back at the board, you'll notice that the C1102 cap is very close to the C1112 electrolytic cap that I just replaced. So I'm going to pull out that C1102, I'm going to wash the board, put in a new cap there, and see if that resolves the problem, which will have to be the subject for another video on another day. So with that, I once again include the many acknowledgments I'd like to make. I'll just leave them here. If you want, you can pause and have a look through. There are some really great people between YouTube, Facebook, and maybe certainly other online and social media sources to get through this. So excellent ideas, and some of these people gave me some other ideas that I'm going to look into for another video, but I think I have to stop somewhere, so I'll stop here.